What's your grade in class?
Hey, let's do this together. While you're talking about me, pull over my camera. Okay, so again, I have also started recording my screen. So I will try to put them on Canvas. Yes, it takes me a few days, but yes, I will try to do that. Okay, so we have this thing. It's a little bit small right now. What did you decide we should write the formula as? C? How many C's? Okay, what else? Hydrogen. Okay, 4 of those. Yep. Good. Okay. So this one, we have to remember that it goes carbon, then nitrogen, then hydrogen fits between those two columns. So it's like hydrogen is actually like 7.5. Okay. So just make sure that you get the order right. I think the hardest part of this is that the order, you need to remember the order. What happens if I have sulfur and I have oxygen? Which one should go first? That's the sulfur. Sulfur should go first because it's lower on the periodic table. It's bigger. Okay, good. So be careful about remembering those rules for the final. How do you guys feel about that? You feel like you could do that on the final? Good. Good. And then counting isn't too bad. And then as long as you can use this key, that's also not too bad. All right, let's look at our schedule. I made one for December. I don't think I handed it out yet. So let me hand out this December schedule so we kind of know where we're going. On Friday when you come back, we're going to do lab 3. So we'll take a minute and we'll talk about the pre-lab. We'll just jump through the pre-lab really quick. So if you want to put the pre-lab up, we will talk about the pre-lab. Okay, so looking forward, we are talking about chapter 6 for the second day. Then we're going to talk about chapter 6. We'll do lab 3. We'll talk about chapter 6 again. We'll have lab 4. We'll do a review. Alex, chapter 6 is due the 11th of December, so be working forward to that. And then we'll have our chapter 6 exam on the 13th of December. Then we'll start chapter 7. Then we're going to do one more lab before Christmas winter break. Okay. Questions on our schedule? That's kind of where we're going. We have lots of labs we're trying to catch up from me being gone during quarter 1. So I think after, we'll still have to do quite a few. By the end, we'll have to do 12 labs. So we're getting there. Okay, we're going to talk about these Alex topics. So
do we do the labs before?
Oh yes, thank you for reminding me. I just forgot. Yes, I have it pulled up here. I just forgot. Thank you. Back to the pre-lab. Thank you for bringing me back. So on Friday, we're going to do a separations lab. So you're going to have to separate. I'm going to give you a mixture of salt and sand. You have to separate that. And you're going to try to figure out the percent composition. So there's 4 different compositions. And then we're going to compare our data. So part of the lab is you'll get 2 points for putting your data onto the group sheet. And I don't think I've linked that yet, but we will. Okay, so let's go ahead and look through the pre-lab together. So these first 2 questions are asking about different types of mixtures. Does anyone know what a homogeneous mixture is? What does that mean? Huh? Oh, what is a homogeneous mixture? What is that homogeneous? Yeah, so this one would be something that's uniform throughout. We only have one type of thing. Yeah, good. So an example of a homogeneous mixture is like salt water, because everything throughout is mixed well. You can't really tell the difference. It dissolves really well. It's very uniform. How about heterogeneous? Good. We have a mixture, and this is something I think of like a chunks. If I have like a smoothie and it has big chunks, or like a muffin, we have there's a mixture, but there's different pieces of the mixture. It's not well distributed. It's not uniform. Okay. The next one talks about, so it's asking about filtration. So in the lab, we're going to do two parts. One part is we're separating sand and salt. And the other part is we're going to do chromatography. We're separating the dyes in a marker. So filtration, we are going to use to separate the sand and the salt. So salt water is our solution that we're separating. And then sand is the solid. So would that be, if we have salt water and sand mixed together, is that a heterogeneous or a homogeneous mixture? That would be a heterogeneous mixture. Yeah, good. Good. Okay. And then the salt water would be like a homogeneous mixture. Did I skip this one? Okay. Number 4. In this lab, evaporation is used to separate what things? So if we're trying to get the amount of salt and the amount of sand, so when would we use evaporation? To get can you say that again?
Like separate the salt water.
Well, yeah. So if we evaporate the water and the salt, that will. If we evaporate the water from the salt, then we can separate the water and the salt. We will be also evaporating the water off of the sand. But I think this is asking about separating the water and the salt. If we use evaporation to evaporate, we'd have to figure out either the salt or the sand. And we could heat it up to the correct temperature, and one of them would evaporate. We're not doing that. We're just going to evaporate water. These two. Oh, you're good. Oh,
Wait, what was number 3 again? Separate the sand from the salt water?
Filtration? Yes. Okay, then I've drawn this beautiful picture over here. So we're going to separate the dyes in a marker. Okay, this is a beautiful picture of chromatography. So what you're going to do is you're going to have a paper. So this is what it looks like. And we're going to use some chromatography paper. Okay, how many of you have done chromatography before? Okay, good. So you're going to draw a pencil line. Okay, this is the starting line. This is like, we're setting up a race. So we're starting here. I should probably draw this on my board. I just realized that. If I draw it on that board, then if I'm recording it, then you can't see it. Let me put it up here. So we are going to use a chromatography paper. We are going to put a pencil line.
your instructions say this needs to be 2 centimeters, and you can read the instructions when you're in the lab. This is where you're going to start. This is like your starting line. And then you're going to put marker right over the top of this pencil line. The marker is going to move. The pencil will stay. The pencil won't move. The pencil is not soluble in the liquid that we're using. So this paper is called our stationary phase. And then the liquid we're using, we're going to put this into some kind of, the instructions are kind of tricky. Some of them say a beaker, some of them say a test tube. So we can probably use either. We're going to put it in a container and we're going to fill up just below the liquid level. I think it says just 10 milliliters. We're going to use rubbing alcohol because the marker is a little bit soluble in this rubbing alcohol. And this rubbing alcohol, that is our mobile phase. So how many of you have put a paper towel in water and the paper towel starts wicking up the water? Have you seen that before? Yeah, great. So that's what's going to happen with the rubbing alcohol. The rubbing alcohol is going to move up through the stationary phase. So that's what's moving. The rubbing alcohol is moving, and that's why it's the mobile phase. Okay. This is also called isopropyl alcohol. So either of those, that's the same thing. I think we're going to use this because that's what I have in the cupboard. This is what you'd like buy at the store. This is what it would be called if you buy it from the chemical company that we buy chemicals from. Okay, so then your marker line is going to start moving with the rubbing alcohol, and some of the marker will be stuck more to the stationary phase and some is going to be more attracted to the alcohol, and it will move up through the paper and it's going to end somewhere. Okay, so then you are going to measure how far. This is going to be the starting point, and then the ending point is wherever the dye gets to. So some of the dyes might end up like here, some of them might end like here. So you're going to measure the difference from where you started to where you ended, the dye ended. So you have to decide where the middle of that dye is. Where did it end? Okay, does that kind of make sense? Okay, let's go back to the questions. So what chemicals are the mobile phase? The mobile phase is rubbing alcohol, or you can put isopropyl alcohol, either of those. Does this go back to that's very confusing. You're not supposed to let something boil. So when you add water to the sand and salt mixture, you're going to heat that up to make sure that all of the salt gets dissolved. So you are going to make sure that that doesn't boil. You're going to heat up the sand, salt, and water mixture. You don't want that to boil because if you boil it, usually when things boil, they splatter, and you want to collect all of the salt and all of the sand that you can. So if you are letting it splatter all over, then you're going to be losing material, and you won't get as good of a percent as you should. So don't let the sand, salt, water mixture boil. But you are going to heat it to make sure all of the salt gets dissolved. Okay. The last question says, you measure the distance each color has moved. Where should you start? Where should you end this measurement? So you're going to start where you started the color. So you should have marked it with a pencil. You're going to put a marker line right across the pencil line. That's where you start. And then wherever the dye ends up at the end of your experiment, that's where you're going to end your measurement. Okay, does that kind of make sense? Okay. All right. So hopefully you have done your pre-lab. If not, make sure you do it before Friday so that we can go right into the lab and get this done. While you're finishing up, I'm just going to let you know that some of the lab takes a while, like heating up the water. It might take a minute. So while you're doing that, do something else, like go to the next part. Get your mobile phase ready. Get your chromatography paper ready. Okay. So there might be some sitting and waiting, but you can do stuff while you're sitting and waiting. Okay. The other thing is we might have to, for this lab, I'm not sure, because we need the sand to be dry, we're going to try to use some hot plates to dry the sand and the salt, but because we don't have an oven. So we might just leave our samples and come back on the review day and measure the weight again. So just if we don't get done with the lab on Friday, we'll just come back next week or the week after. Okay. Questions on that? Are we good? Okay. Oh, I'm here. Okay, so let's go back to our chapter 6. We're going to try to get through a few topics today. Do we get out at the 40? Is that? Okay. Let me check to make sure that I'm a little bit honest. Yeah, 40. 9:40. So watch for that. So we have to, this next topic is asking for an uncatalyzed and a catalyzed reaction. Hello. And we need to look for what type of reaction it is. This one is endothermic. So let's remember what an endothermic and an exothermic reaction looks like. Okay. So hopefully you remember. Let's see. So we need an exothermic graph and an endothermic graph. Does anyone remember what an exothermic graph looks like? What's the key points? Good. The products are lower than the reactants. Exothermic. Heat is released. And then endothermic is just opposite. That's the key. The products are higher than the reactants. And then we have this transition state. Okay. So this is just a regular chemical reaction. Yes. And then this question that we're looking at is asking about a catalyzed reaction. So a catalyzed reaction just makes the reaction happen easier. So we have the same starting point. I'm not going to draw right on my black marker. It's going to make my pink marker black. So we're going to start in the right spot, same spot. We're going to end in the exact same spot. But when we have a catalyzed reaction, the activation energy is lowered. Okay, so we have the same reactants and products. The energies of the reactants or products are the same, but the activation energy barrier is lower. Okay, so this one would be catalyzed. So same thing on endothermic. Reactants are starting in the same spot. Products are ending in the same spot. Just the activation energy, the barrier height is lower. Okay, so catalyzed. Okay, questions on that? Does that kind of make sense? So that's what we have to do. So for this question. So the first thing that we need to watch out for in this question is we need to look for what type of reaction. This one is endothermic. So we just have to pick something. It doesn't really matter where they go, as long as for endothermic, the reactants are higher than the products. So reactants are somewhere, products are higher than that. Okay? And then uncatalyzed, we need this to be higher. Okay, that's not going to work because I need the catalyzed reaction to have a lower activation energy. So I'm going to put it like this. So right now my reactants are here, my products are higher, and I have an activation energy. So this one, my catalyzed reaction, I have the same energy for my reactants, I have the same exact energy for my products, but the activation energy is lower. Okay, I do need to have a barrier a little bit, but it just needs to be lower. Okay, so kind of play around with that. That's the key to this question. Okay, let's do one more, just for fun, really quick. These ones should be pretty straightforward. I'm not sure. Not a lot of people miss this, but still people miss this, and I feel like this one, no one should miss this one. So this one says exothermic, so watch for what it's saying. So products need to be lower than our reactants, okay? And I'm going to do the same exact reactants and products for the catalyzed reaction. And then the uncatalyzed reaction has a higher activation energy than the catalyzed reaction. Okay, so watch out for those things. Questions on that? So that's all that you have to do. Make sure your products are lined up, reactants are lined up, activation energy is lower. Make sure you're drawing correct. Is it exothermic or endothermic? Questions on that one? Okay, so catalyst is just something that makes the reaction more favorable. The energy barrier goes down. It's not a reactant, it's not a product, it doesn't get used up, it just makes the reaction happen under more favorable conditions. Okay, all right. The next one we need to talk about is we're going to start talking about equilibrium, and we'll see how many we can get through today. But we are going to take a few notes so that we know what equilibrium is, and then we'll go back to Alex and talk about some of the questions. So you don't have to write down everything. This is just some ideas. Write down what you think is going to be most helpful to you. So in chemical equilibrium, the concentrations are constant. At equilibrium, the concentrations are constant. They stop changing. And the other key for chemical equilibrium is the rates are equal. And that will come up in one of the Alex topics that we look at. So the rate of the forward reaction is equal to the rate of the reverse reaction. That's the definition of chemical equilibrium. This is kind of confusing to think about in a chemical sense. So some other examples in real life are like, if your bank account is at equilibrium, that means you're getting paid the same amount that you're spending. Stuff is going in, stuff is coming out of your bank account, but the balance is remaining constant. So that's the same as chemical equilibrium. The reaction is going forward, the reaction is going backwards, but the concentrations aren't changing, the amounts. Okay. Another example is a water level at a lake. So if the inlet flow is the same as the outlet flow, your lake level is going to be the same, but you're getting new water circulating through that. Okay. So those are some examples of equilibrium, and that's kind of the definition of equilibrium. So when we're talking about equilibrium, we have to be talking about a reaction that can go forward and reverse. So not all reactions can do this. Like if you think of like a combustion reaction, that's not one that really goes backwards. But some of these other reactions, especially in water, reactions can go forward and they go backwards. So if it's a reaction that's happening in a solution, it's reversible. So we use this little arrow down here. It's a double-headed arrow to tell us this is a reversible reaction. This is something that we could reach equilibrium with. Okay. The other important thing is that we have to have all of the products and the reactants to be reversible or to be at equilibrium. So if we, at the very beginning of the reaction, when we just put in our reactants, that can't be at equilibrium because we only have our reactants. We have to wait for a while until we build up some of the product. And that will also come up in one of the Alex topics that we look at. Let's see. Okay, so this is just talking about if we have, what is this talking about? Rate goes up with concentration. So if we have this reaction, A plus B goes to C plus D, and we increase the concentration of the reactants, the reaction is going to speed up forward. Okay, if we end up, for some reason, we add more product, then now we have more product. Now we can make more reactant. So the reaction is going to have the reverse rate go faster. So if I add more A, then my reaction can start progressing towards the product more. If I add more D, the reaction can go back towards the reactants. Okay, we'll talk more about that. All right. This table is from Alex. I don't know how helpful it is, but let's just walk through it. So If the forward rate, so when we're talking about the rates, we're talking about this is the forward rate going from A to B to C to D. The reverse rate is C to D, the products going to the reactants. Okay, so that's what we're talking about. So when the forward rate is greater than the reverse rate, that means we're losing reactants. All the reactants are starting to form the products, and we're getting more products if the forward rate is greater than the reverse rate. And then the opposite is true. If our reverse rate is greater than the forward rate, then we're losing our products more than we're gaining our reactants. Okay? And then at equilibrium, this is our definition of equilibrium. When the forward rate equals the reverse rate, then that is at equilibrium. We have a constant concentration. We could have way more products than reactant, that's okay. But if the rates are equal, then our concentrations are going to stay constant. Okay, questions on this? And I think if we do some examples, this will make more sense. Okay. Okay, let's go to our Alex topic. So we're going to do this one. Predicting relative forward and reverse rates of reaction in dynamic equilibrium. Okay, so there's a few of these types of questions. We're going to do, it says, okay, acetic acid and water react to form hydronium cation and acetate anion like this. Imagine that you have 169 millimoles of this thing. What is this one? This is acetic acid. This is a reactant. So you have to figure out, are you adding a reactant or a product? Okay. And it's removed. We're not adding it from a flask containing a mixture of this. So notice we have all of our reactants and our products. So we could be at equilibrium if we have all of the reactants and the products. Oh, and it says that's at equilibrium. Then answer the following questions. What is the rate of the forward reaction before any of the acetic acid has been removed? So think about right at the beginning of this question, what is going on? So we have all of these things in a flask and they're at equilibrium. So at equilibrium, the definition of equilibrium is that the rates are equal. So the rate of the forward reaction is going to be equal to the rate of the reverse reaction. Does that make sense? That's our definition of equilibrium. So before we do anything, we came across this reaction. It was at equilibrium. We haven't done anything yet. It's at equilibrium. The forward rate is equal to the reverse rate. Okay.
Is it always that?
No. Sometimes we'll look at one. Sometimes the flask is empty. If the flask is empty, the reaction rate is 0. Nothing is happening. So just kind of walk out for that. What is the rate of the forward reaction just after the acetic acid has been removed from the flask? So right after, you remove. So we have to figure out where this is. This is right here. Okay, so if I'm removing this, what's going to happen to the reaction?
This.
So we're going to have less of this. So what happens is the reaction wants to go back to fill in. This is like creating a vacuum, kind of. So we removed something. Now our products are going to try to balance that missing reactant. So the reaction is going to shift to fill in what we pulled out. Okay, it wants to go back to equilibrium, and the only way it can do that is if it makes more of the reactant that we removed. So initially, right after we pull this out, it's going to increase the reverse rate. So that's going to mean that the forward rate The forward rate is less than the reverse rate, just initially. Okay. Then it says, what is the rate of the forward reaction when the system has again reached equilibrium? So this, we've waited for a while. We're letting the reaction sit. And now we're at equilibrium. So the definition of equilibrium is the rates are equal. Okay. So greater than 0 and equal to the rate of the reverse reaction. Anytime it says equilibrium, you're going to put that they're equal because that's the definition of equilibrium. The rates are equal. Okay. All right. And then the last question says, how much less of the acetic acid is in the flask when the system has again reached equilibrium? This is a little bit confusing, but it says we took out 169 millimoles. So initially, this reaction is missing 169 millimoles. But then the reaction goes to shift, it shifts to equilibrium. So to balance, the products start forming the reactants and we'll start forming some more acetic acid. So we're not going to be missing 169. We'll be missing some, but not as much as that. Does that make sense? So some, but we won't be missing 169. We'll be missing less than 169 because our products formed our reactants. Does that make sense? Okay, this one's tricky because it's not like a formula you can just type in. You have to like reason through it. But there's quite a lot of patterns.
So what if you're adding to the flask? Like,
So then, yeah, let's see if this one's added. So if you add something, the reaction's going to shift away towards what you add. It's like you just got a whole bunch of new material. That material can be used to form product. Okay, so this one says acetic acid and ethanol react to form ethyl acetate in water like this. Imagine 239 millimoles of, this one is ethanol. Oh, no, not ethanol. This is ethyl acetate. So that is a product. Are added. So we're adding a product to a mixture of all of these things at equilibrium. So we have a flask, it has all of these things, it's at equilibrium. What is the reverse rate before any ethyl acetate has been added? So you come across the system, it's at equilibrium. So what's the rates? Equal. The reverse rate is equal to the rate of the forward reaction. Good. I don't know why they all say greater than 0, because I don't know. They all say that, so I don't know. That does. Okay, what is the rate of the reverse reaction just after we add this? So think about what's happening. So we just added ethyl acetate. The reaction wants to shift away from what we added. Okay, so it was balanced. So it's going to shift. Yeah, the reverse reaction is going to be greater than the forward reaction initially. Yep, to balance. So greater than 0 and greater than the rate of the forward reaction. What is the rate of the reverse reaction when the system again has reached equilibrium? Equal. Good. And anytime it says equilibrium, you put equal. So if you get all of these wrong, don't get all of them wrong. Make sure you put this one is, anytime it says equilibrium, you should make sure that you put it equal. So get at least one of those. How much more is in the flask when the system has again reached equilibrium? So we added this much, but some of that went to form our reactants so that the reaction became at equilibrium again. So how much more is there? Well, there's some there, but there's not 239 because some of that 239 went to make the reactant. Okay. All right, questions on that one? Okay, let's see if we can find one that says it's empty. Let's try another one. Okay, so this one's a little bit different. You have to watch out for this one. This one says, imagine, okay, we have hydrogen and chlorine gas, and they make hydrochloric acid. Imagine we have 240 millimoles of hydrogen HCl are added to an empty flask. So this is important. Make sure if it's empty, what's happening before you do anything?
0.
Good. The rate is 0 if you don't have anything in your flask. That's the only time it can be 0. If there's nothing happening there's nothing in your flask, then it can be 0. Okay, what is the rate of the reverse reaction just after HCl has been added? So we're adding a product. So the reverse reaction will be greater. It's trying to shift away from what we add. So greater than the forward reaction. What is the rate of the reverse reaction at equilibrium? Good, greater than 0 and equal to the rate of the forward reaction. That's the definition of equilibrium. And then last question, how much HCl is in the flask at equilibrium? We've added this much. Some of that went to the reverse reaction to form the reactants. So good, some but less than 240 millimoles. So hopefully you're starting to see some patterns for these types of questions. Good. Okay, we have 15 minutes left. Let's talk for a minute about equilibrium, this other thing in equilibrium. We'll talk about equilibrium constant expression, and then we're gonna go through this. Why is this not going? That's not the end. There we go. Okay. Concentration is going to come up in this chapter a little bit. So this is the definition of concentration. It's this is the units that we use. Concentration is just how much of something is in a volume. Okay. In chemistry, we are going to use molarity as our standard unit. So big M is molarity. Big M is our units for concentration, and that is moles per liter. We don't really have to do too many calculations with that, but it does come up in this chapter, so I want you to know what are they talking about when they're talking about concentration. It's just how many moles of something per liter. Okay, it's like how much orange juice do you add per how much water do you add. And again, I don't think you have to calculate anything with this in this chapter, but when they are talking about concentration, that's what they're talking about. Okay, so we have some kind of chemical equation, and we need to write the equilibrium expression. So this is how we do that. This is our reactants and our products. These little numbers, or the little letters, are the coefficients, okay? So when we write the equilibrium expression, we're going to take the concentration. So these little brackets, these square brackets are representing concentration. So we write the concentration of C, and then we put the coefficient in front of that product. Okay, and then concentration, that's what these brackets are, concentration of D, the product, raised to the coefficient for D, okay, over concentration for the reactants, each raised to their coefficients, okay? So I think the thing that helps me the most is the equilibrium expression is the products over the reactants. And then I can remember this part, concentration raised to the coefficient, concentration raised to the coefficient. But sometimes I have a hard time remembering which one goes on top. So products goes on the top, reactants goes on the bottom. This is products over the reactants for equilibrium expression. So there's two types of questions. We'll look at this in Alex together. There's two types of questions that show up. One is if it's a concentration problem, that means it's in solution, so in water or aqueous. Or we could also have a pressure equilibrium expression. So this is, a lot of your questions are like, oh, you have some stuff in a reactor. And what they're talking about is usually a gas reactor. And all of your reactants and all of your products are gases. So when you do it, if it's a equilibrium constant expression, a pressure one, then you just have to put the pressures in parentheses. So the pressure of C raised to the C, the pressure of D raised to the D. And You just put these in just regular parentheses. Okay. And again, this is products over reactants. Okay. All right, let's do one of these together, and we'll see where we are after that. See, this is writing a concentration equilibrium constant expression. Oh, this one just comes. Great. Okay, let's see if we can make this a little bit bigger. So equilibrium constant expression. So we're going to have a fraction. We're going to take products over reactants. And we have to put this in our brackets of its concentration. So the concentration of this product, it doesn't matter the order, as long as products are on the top. So H plus is my first product. And then I'm going to put a bracket. And this is to the 2, because there's a coefficient in the front. That's where my exponents are coming from, okay? And then that would be multiplied by the concentration of this carbonate anion, CO3, 2 minus. So the other thing is, write this exactly how it shows up in the equation. Don't make stuff up, don't add stuff. Just write the chemical. This is H plus, this is CO3, 2 minus. And then if it has a coefficient. This doesn't have a coefficient, so it would be raised to the 1, but we don't have to write that. And then over the concentration of our products, this is, I don't know, this is bicarbonate, H2, CO3, bracket. And that is our equilibrium expression. Okay, so not too hard. You just have to know products over reactants. The exponent comes from any coefficients you have. Okay. All right, let's try another one. Okay, this one is just long. There's nothing too fancy about it. Okay, so I'm going to put a fraction, products over reactants. So I'm going to do CH3Cl in my brackets. So the concentration of methylene chloride times the concentration of hydroxide, oops, the wrong bracket, OH minus, bracket, all over, we have 2 reactants here. This is methanol, CH3, OH, bracket, times the concentration. So the brackets, again, those are representing concentration. Cl minus. We haven't used that yet. Bracket. Okay, this one didn't have any coefficients in the front, so they're all, the exponents are all 1. So that one's not too bad. Okay, so just be really careful. This is just like you're copying down what they have. You just have to put it in the correct spots. Okay, so don't make up stuff. Let's do another one. This one's boring. We're gonna try another one. Let's try one. Do they only have 1 exponent? Oh, okay. We'll try this one. This one's really long, but we can do it. Okay, so this one we have, this is our product, C6. Oh, this is annoying. C6H10. O4. So the concentration of that, there's no coefficient, so this just gets a 1 exponent. I don't have to write that. And then this one is OH minus. The coefficient for this one is a 2, so I'm going to raise it to the 2. And then over here we have, so remember, reactants on top, products on top, reactants on the bottom. So reactants over here. So we've got CH3, subscript 3, COO minus. So we're just copying down exactly what the reactant is, put the correct bracket. And then to this one has a coefficient. So that coefficient becomes the exponent. Then the other thing, C2.
Are they all affect the same It's like same.
Yes, same pattern. Yes. What's that? Is that, I think, yeah, they're all like this.
Just okay.
Into H6O2. Okay, questions on that? Do you think you could do that? Okay. All right, so we got through 3 topics today. We'll have one more day for chapter 6, so we'll get through 3 topics next time. We'll stop here. We've got 5 minutes left. Make sure you have your pre-lab for lab 3 done before you come next time. We'll do the lab 3, then we'll do chapter 6 the next time. Okay. All right. Questions for me? Okay. You have you have about 7 minutes of work time. Yes.
So I can get all these, but I'm a little confused on this.
Okay. So you added, you added 139 millimoles.
Mm-hmm.
And then some of that converted to,
So some WS.
yes, I think it's always that.
See, I did that with another one, but it was wrong.
Oh.
So, but maybe, I don't know, let's see.
Oh, because it's empty.
Oh.
Are you good?
Yeah,
Oh.
yeah, let's keep doing it.
Okay. Would you have a question? Did I see your hand? They didn't have to have a question.